Hi everyone, my name is Hao Zhu. I'm a PhD student in the System Network Engineering group of University of Amsterdam. The work was done with the help of Jose Azana, Castellat, and Paulo Glosso. The topic is green routing in software-defined data center networks based on the openness. Today's networks, such as the Internet, plays an essential role in society, but they consume quite a lot of energy. For example, the energy footprint of data center network is 10% to the 20% of total energy consumption. If you think this number is not very big, the proportion could be up to 50% if the power management techniques are used on the server side. Moreover, the growth of global data traffic speeds up the increase of energy demand in networks. Global cloud IP traffic will be 3.9-fold from 2013 to 2018. In addition, networks suffer from efficient power usage because of the overprovision to guarantee the high capacity and robustness. It is therefore essential to reduce energy consumption of networks. Green routing are effective approach that can fix this problem. Green routing lowers the energy consumption and cost of the CO2 emission of the network resources on our path. This is different from adopting shortest routing paths with the best performance target. A network provides managers a network where servers utilize diverse types of sources of energy, such as wind, solar, and coal. If a user requests a path to migrate VMs between the servers, it would be good if one could determine which among the possible paths is greener and then switch off unused network components. Now the question is, what's the most effective manner is to achieve green routing? There are two ways to implement energy-aware routing. One is in IP networks. Another is to use software-defined networks. In IP networks, we can, for example, observe the development of the green OSPF based on the OSPF protocol. Its energy-aware algorithm used a subset of shortest path trees to select the routing paths and activate as few as possible links to route traffic. In software-defined networks, on the other hand, routing decision and data forward are decoupled. SDN provides a centralized view of the entire network state, such as traffic and topology. Green routing could be easily implemented in such networks. It is important to note that green routing is more effective when implemented using a network management platform instead of acting directly in the SDN controller plane. There are two reasons for this. First, implements cannot be easily migrated between SDN networks with different types of SDN controller because of incompatible structure and interface. Existing network management platform can support multiple types of controller, and they have no compatible problem with integrating new energy optimizer modular in them. Second, green routing techniques rely on precise information about current topology and traffic, but the capabilities of the open flow controller are usually limited to obtain this information. For example, a NOx controller can only discover network topology, and most of the controllers cannot obtain topology or traffic statistics. Network management platform can provide the capabilities missed in the controller. We decided to focus on implement of green routing in SDNs, and we adopt an existing framework, OpenNAS. OpenNAS is a framework developed a few years ago in a EU-funded project, Matico, that has seen significant extensions and developments afterwards in the context of pan-European networks giant. Now, OpenNAS can abstract the resources to be managed. It defines a vendor-dependent interface to access services provided by these resources. OpenNAS has rich network capabilities. For example, it can offer bandwidth on demand, provide topology discovery, implement many use cases. We can implement more energy-aware capabilities like energy-aware bandwidth on demand by combining the energy monitoring with existing network capabilities in OpenNAS. Besides, OpenNAS has a well-organized structure to enable the abstraction of the network technologies and resources, easily extended to implement new network technologies. And OpenNAS can also take advantage of SDN technologies. That's the reason we want to implement energy-aware capabilities in OpenNAS. We set out to develop an energy optimizer bundle in OpenNAS. This is a dashed component in this finger. In this bundle, we intended to implement a set of energy-aware capabilities. The green routing capabilities in the bundle require knowledge of the flow request, traffic, topology, and energy. Users submit flow requests that specify where they want to move VMs. OpenNAS can provide topology and traffic information. The capabilities about monitoring and provide network information are missing. Therefore, we designed architecture of the energy-aware OpenNAS based on the requirements of green routing. There are three sets of energy-aware capabilities in our new bundle: the energy monitoring capabilities, energy distribution capabilities, and energy-aware routing capabilities. Energy monitoring capabilities obtain and provides an usage information for parameters in the observed metrics. For example, power consumption and consumption, electricity price, and from data statistics in the calculated metrics. For example, total energy consumption and total electricity and energy efficiency. Energy distribution capabilities describe and create metadata about energy source parameters, green metrics, power states, so on in the OpenNAS. We used the energy distribution language ontology for the knowledge representation in domain of the energy monitoring. With the energy distribution language, OpenNAS instances energy information using a common vocabulary and makes information understandable between the software components. The third set of capabilities we developed is the green routing capabilities. Needed to calculate the green routing paths that push the static flow rules for the routes to open flow switch through the open flow controllers. There are two methods to evoke green routing functionalities in OpenNAS. First is the network provides or the user directly sends a green routing request through the GUI to the open NAS. The second is OpenFlow controller detects a packet in event in a switch, then send a routing request to the open NAS server. Based on the architecture of the energy-aware open NAS, we developed a prototype. This prototype includes an open NAS server and the web client GUI. The testbed is a mininet network with a topology consisting of 6 OpenFlow controllers and 5 hosts. The switch had the same network capability and were divided into the 2 groups, controlled by the flat light and open daylight controller, respectively, who have different CO2 emission rates. We assumed the 2 groups consumed solar and thermal energy respectively. We ran the OpenNAS server in the same machine. The steps of the using energy-aware OpenNAS for the green routing are shown in the figure here. Here, you can see the screenshot of our demo. Our demo has 3 main functions. The first is show power information of each node. The second is show energy power information of each specified routing path. The third one is find green routing paths using the 3 green metrics: power consumption, electricity cost, CO2 emission. The green lines in the figure 2 is the routing path we found using the power consumption metrics. Our prototype is based on the emulated resources. In order to test the effectiveness of our prototype, we run a simulation of the B-cube network. It evaluates 3 algorithms: the shortest path, random, and power greedy. Power greedy path finding is the algorithm currently used in our prototype. It finds a routing path for the current flow, which increases the least power consumption for the overall network. We take the maximum of the total number of flows on our server at 100% network load and vary the percentage of the number of flows in the topology to simulate different network utilization. The source and destination of each flow are randomly chosen from the leaf switch. The speed of each flow is uniform distribution, but it has to guarantee the largest link throughput in the network is less than 1 gigabit per second. The first figure shows the power saving of the green routing algorithm against the network utilization in B-cube network. The y-axis here depicts the power consumption of algorithm is how much ratio of the original power consumption. We can find that the power saving becomes less when the lower network utilization, as the less network components are idle, when the traffic becomes more intensive. When the network utilization grows from 20% to the 80%, the power greedy routing only uses less than 40% of the original power, and it can save at most 20% power than the shortest routing. Figure 2 shows the mean flow delay time of the 3 green routing algorithms against the network utilization in the B-cube network. We see that the mean flow delay of the greedy routing increased from 4 milliseconds to the 5.6 milliseconds, while that the shortest routing is nearly stable at the 4 milliseconds. This tells us the greedy routing finds power efficient paths, although that have more hops. Our evaluation results show that the greedy routing algorithm is effective at saving power. It In particular, when the traffic is not very heavy, it can be used at the non-peak time or in a scenario with the tolerant performance requirements. In the future, we expect it to study the trade-off between the power consumption and the performance of network for the routing algorithm. In the end, we conclude our contribution in this work. We proposed an information model which used in the energy-aware bundles, which can describe energy-aware infrastructures. The second contribution is we present a complete power management solution based on the open source network management platform. This is, as far as I know, this is the first try to do this based on the openness. And last, we evaluate, evaluate the effect of network programmability in the overall delivery of a sustainable service. And finally, you can download demo here from the link. If you have any questions, you can send email here. Thanks.